we look at just the deterministic function, it shouldn't be too wiggly, and that's being estimated here. We can then move around our estimated frequency until we get what is a reasonable fit. Okay, so I see it started to go more wiggly at 39. Let's try 38 now. Yeah, at 38 it's almost perfect, so we are getting just that quadratic function back as being the deterministic part. We can also look at the seasonal part of the function, and we see that's being reflected pretty well too. And then the remainder. Okay, and we can believe that that's an ARMA process. So that's one way to use the STL function to separate out the seasonal, trend, and remainder parts of the time series. A lot of it is just playing around and seeing which frequency works best. There are other parameters such as t window and the local regression parameters, which can be varied in order to get the best fit. And let's do this with another example. So here we're going to look at Barclay's closing price data. Okay, there's a smooth periodic. Okay, let's count the number of peaks that we see between 0.4 and 0.5. And I make that as 13 peaks that I count there. So even counting between 0.3 and 0.4, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 12, 13 here. Yeah, so I'll take that as 13. So I estimate the frequency. Remember I've set the frequency on this spectrum function at 1 initially. So I'll estimate the frequency as 5 times 13. And let's have a look at what the output of that is. Let's try that again. Okay, so this is the output remainder process. Let's look at the seasonal estimate. Okay, that's there, difficult to understand. And the trend function. Okay, now that trend function looks much better at fitting the price data that we had before. And I could overload it too. In fact, I think I have done that actually later, so let's do that here. Right, so here we see we've got the green line, which is the seasonal part plus the trend, and the red line, which is just the trend that's been fitted using a low S, and the black line is purely just the price data that we observed. In fact, it's not even fitted to the log process. So if I really do believe that a frequency corresponding to a lag of 65 is what I need, then what's the difference there? I should see a process that is close to being stationary at a lag of 65. And although it's close, I suppose removing the quadratic trend would just make this close to stationary. So possibly this is believable as a stationary time series with the transformation. Let's try transformations such as log. Let's say. Now let's have a look at the remainder process. Okay, now that's much more believable as a